Hello, my name is Hochul Kim and I'll be presenter for this session. I'm currently developing the Explore service and timeline with my colleagues in data science, dev, and ML platform dev teams. And under the topic Explore and timeline from a ML pipeline perspective, I will talk about the meaning of machine learning pipeline and machine learning-based services. This is the agenda for this session. I will first introduce the Explore service. Then I will move on to talk about what the machine learning pipeline means in general. Then I will move on to an explanation of what machine learning pipeline is in relation to the Explore service. And afterwards, as I summarize the session, I will also briefly go over what we have in store internally. So first, an introduction to Explore and timeline. Here, I'm going to divide up my explanation into two sections. First, what is Explore and timeline, and then what is the recommendation system in Explore. As you see on the screen, when you access Timeline by clicking on the Timeline button on the bottom middle section of the screen, you can access the Timeline's Explorer service through the areas marked on the images on the left and right. When you go into the Explorer service, the main page of the Explorer service is displayed as you see here. Compared to how Timeline was, you can say that the UI is intuitively different. That is to say that the main page of Explorer now shows several posts at once. Users and posts are the basic units of composition in both Timeline and Explorer, but Explorer only displays post and no user information, which is its difference from Timeline. Providing personalized posts that users may like is what we call the Explorer recommendation system. As an additional scenario, when a post is selected in the main page, the post related to the post clicked is displayed as you see here. The fact that the user chose this post could be understood as that the same user will like similar posts in the future, and taking action when the related post is shown can also be understood the same way. Therefore, during model training, logs containing these kinds of information are taken into account to carry out recommendations. Regarding the recommendation logic, Ji-Hong Lee from the same team as myself presented in a session in last year's Dev Day, so I think you can refer back to that session to learn about the basics of recommendation. If you refer to the service scenario that I showed you before, you can find the information that can be used for the recommendation system. First, information such as the user's preference or category can be deduced based on an action taken by the user related to a post. And second, content-related information from the post can also be considered to be very important. Additionally, because Line has many family services, we also utilize the data generated from these family services as well. If I take a step further and explain to you the flow of the recommendation service in Explorer, first, there is data that I have mentioned in the previous slide, including users' actions. Such data are both directly used, or these data are converted into a new form to create a feature, which in concept describes the characteristics or features of users and posts. The data generated is monitored and goes through filtering to filter out harmful or sexual posts. And these are all put together to train the model used for recommendation. Then the result of recommendation is retrieved from the model through the API, and by reflecting the filtering information in real time, the service is provided to the user. I've divided up the flow in this manner to show in a macro perspective that this is how the Explorer service is structured. The structure looks simple and not at all complex when you just look at the image, but considering the huge size of data, time taken to train the model, resources used, and limits to how complex the model can be, and most of all, the service restrictions, the process is not as simple as how the image makes it look. I will talk a little more about this in the following slides. I'm going to try to understand the previously mentioned problem from a machine learning pipeline perspective. I'm sure some of you may feel puzzled because I'm suddenly talking about machine learning pipeline while I was talking about the Explore service. But it is a topic that must be handled in order to continue talking about the Explore service. Because there seems to be no widely known definition of the ML pipeline, so I tried to give it a definition. As you can see from reading it, you can think of ML pipeline as a series of development processes that not only deals with data, but something that can involve many elements to be provided as a service. So the ML pipeline is data-driven, but is not a data pipeline. So in other words, it needs to understand the domain knowledge, but should not simply generate data. Ultimately, the goal is to provide a service, so consideration and understanding of the service environment is needed. What needs to be considered here is that each task is high in cost in terms of time and complexity. And lots of calculation resources are used in modeling, and a lot of resources are needed for simple tasks such as data labeling, among others. Each of these tasks are carried out separately, but they all serve the same goal, which is to provide a service. To explain what I have just said, as an example, let me take the Timeline Explorer service. If this service had to be categorized, it is also a service based on machine learning. And I think we first have to think about the difference between machine learning-based service and conventional services. The focus of the traditional database services is getting a good output based on data. In other words, because there is a well-organized and proven logic and data tailored to it, there is no need to directly handle large volumes of data during the service process. And to exaggerate, all the service has to do is to make sure that data is well stored, so there's no problem in its use. But machine learning-based services require an additional step where the model has to be made. And certain data model created from a certain result is added to the machine learning-based service, and this is the focus of machine learning-based service. But because even machine learning services also have to be provided as a service, it is difficult to see these two services as completely separate entities. As I have marked down in this image, there is a part in machine learning service where a service is provided in the usual way with machine learning added to part. And therefore, we not only have to think of a way to provide this as a service, but also have to consider what happens when machine learning is added. I've listed out the related tasks that I think are needed. These tasks can be seen as belonging to data science and machine learning versus system and infra categories. I don't know if you have noticed, but we are missing the task related to the core logic of the model. Of course, I'm not saying that the model's core is not important. Of course, in a machine learning-based service, a model trained through machine learning is the core, but in this image, I just wanted to emphasize that in order to provide this as a service, many things have to be considered beside the core logic of the model. So if we organize this a bit more, we could organize the task like this. Like a data pipeline, it proceeds in the order of data flow. But its biggest difference from a general data pipeline is the part where the model is trained and served to provide the model as an actual service. Now I'm going to take Explorer's recommendation service and explain the ML pipeline. And in this chapter, I'm going to first introduce the infra that we're using, explain how the infra is used in each step of the pipeline that I've shown you before. And then I'm going to show you how ML pipeline approach method is used in an actual model by showing you some examples. The infra we use in our team can be summarized using this image. Largely, we have data clusters which make collection, storage, and computation of large volume of user and content data possible. We also have RDB, MySQL and Redis, which allows a quick access to data during serving. And we have storage for storing objects such as images and videos. There's also the Jupyter environment for data analysis and data modeling and serving cluster. which serves based on what is in the Jupyter environment. And when it comes to the various operational issues, like, delete certain posts, include certain posts, these are filtered using a logic. And finally, the actual Explore service is provided to the user through an API. If we take a closer look at the system resources, we have the Hadoop-based data cluster, which stores and handles the log data as it is. And for this, we use the Hadoop HDFS or Hive provided by the IU, which is used throughout the company. And we usually access it through Spark. And for data analyzing and training, we use the Jupyter environment on cluster. And for this, we use Utopia, which was developed by our team for an easy use of a relatively large volume of resources. Actually, Utopia plays an important role in analyzing and modeling. For more detailed information about Utopia, you can refer to a separate session prepared by our team. And the other steps involved in serving the RDB, which allows for a fast access to needed data, and in-memory DB is used depending on the situation. And the actual serving is done in the form of a Kubernetes-based container. So you can think of it in a manner that each individual model is served as a single container. And through Clipper module, the cluster's model container is bound and served by mapping the API. The tasks that go out in the service as these individual processes are individually split and automated through Airflow. Now, I'm going to explain the individual steps. So I will explain each step you see in this image. First step is, data collection. And in this stage, we collect the data that is used for training and serving. First part of this step is defining the data to be collected with the domain expert. With Explorer, it mainly looks at users' clicks and content data, and log type data are basically stored in large volume in clusters. And video, we retrieve it from object cluster. In case of this kind of cluster, we use an internal platform, the IU, and the data we need for actual serving are sometimes stored separately in RDB or in memory DB. We also need a separate storage to store objects such as pictures and media, and for this we use OBS, which is also an internal platform. And the next step, which is data analysis, the data that was defined and collected are analyzed. Largely, we verify that there is no problem in the data itself and analyze the form of the data. Afterwards, we analyze the meaning of the data, using EDA and visualize the data. Data is analyzed through the Jupyter Notebook, so the analyzation and visualization of data is not difficult. Just specifically, the environment the notebook runs on, the Jupyter service environment, is structured so that it can easily access the clusters such as data cluster, MySQL, Redis storage, to minimize the difference between data used for test and research and the actual data. Once data analysis and verification is done, we move on to the feature engineering and extracting step. Here, raw data or other metadata are processed to create new features. If data is processed in real time, Kafka, Spark are separately executed and processed, but when the execution is done by hour or by day in batches, Jupyter Notebook is used for processing. The features generated in this way are stored in Hive or HDFS as a default, and as mentioned before, if it is needed data that needs to be used by services right away, then we also use MySQL or Redis. Once the feature is prepared, we train the ML model for recommendation. Currently, modeling is done through the Utopia, the Jupyter Notebook environment, so the needed resources can be conveniently assigned. The model for now is trained on a fixed cycle, and we prepare so that the notebook created here can be seamlessly served when needed. During the serving stage, the model created through the modeling stage and notebooks created through inferences are made into a container for serving. And if more data is needed for inference, the data is pre-stored in MySQL or Redis. The data required in the actual serving stage are generally data that needs to be quickly accessed and used. So the data is either held by the model or is retrieved through DB or the Redis. The production stage could be called the stage when service can be actually used. There is an API server to efficiently support monitoring A/B tests and so on. A serving container is connected through the API server for serving. In this stage, filtering and other information necessary from an operational perspective are also referenced, so you can think of this stage as the stage where the service goes out to the users. Even if the model does not act normally, some action must be guaranteed, and we're making sure that many operation requests can be processed as well in this stage. Here, I've organized it to look very simple, but many tasks are involved, and currently in Explorer, as I mentioned before, Airflow is used to define and organize the dependencies between the tasks. The nature of each task and the platform it needs are very different. But some of the tasks do depend upon one another, so each task needs to be automated and scheduled, and Airflow is used to this end. Automation is a big task, but if we did not do this, the necessary tasks that has to be done for machine learning-based services, which are data analysis and model development, if the tasks mentioned previously are not automated, a lot of resource is wasted. So that is why we are automating these tasks. This is a sample screen from Airflow, which manages many tasks. It's one of the workflows for deploying an actual service, and it manages tasks from the start to finish, from data verification, generation, modeling, and deployment, all on one page. Each individual square is a separate task, and the tasks are managed so that each task is executed sequentially at a specific time. Aside from order management, require time and so on are managed in the Airflow. So it helps us greatly in task automation and deployment. Next, I would like to talk about the pipeline using some case study examples. Among the tasks, certain tasks do not match the concept of a pipeline perfectly and some do. So I will try to use different examples. First is the following embedding case. I think I will first have to give you some background information. Previously, we generated embedding about a user. For instance, if we had prepared a post to recommend, this means that we created embedding about the user who created that post. This means that we hadn't secured embedding for all of the users, so it was difficult to say that we had achieved a full personalization. And at the same time, using the follow relationship as the standard, so we reviewed the idea if we could use the data such as A followed B as a feature, and we reviewed the idea that whether this could be made into models. And this is what that conversion process looks like as an image. So each arrow is a number, it's displayed as an arrow. This is the goal we had for development. In conclusion, our goal was to express the user's following data as an embedding so that if the embedding have high similarity, it could be said that these users are similar, they are following similar users. So I am going to talk about steps in the flow that I mentioned earlier. First is the data collection stage, which I showed earlier. The part that is different here from the previous image is that because the follow relationship data was already defined, so we could collect this data right away using the common data cluster. And actually using this method, a lot of time can be saved in data collection. In the data analysis stage, originally, we verify the data itself. And in this case, we analyzed whether the follow relationship data is meaningful. For instance, we analyze data such as the number of people a user is following, or the average number of followers, or whether the influence of influencers with many followers is significant, and so on. So you can think of the task in this stage as task verifying and checking whether a certain data will be useful as a feature. In conclusion, we decided that it is okay to create a feature out of this data, so we moved on to the feature engineering stage. And in the feature engineering stage, these tasks are carried out. And in case of follow embedding is generated, you could say we tested out several models. So the form we originally had was data in a graph form. So we tested out models which convert this graph form data into embedding. And because we were able to secure a lot of data, some tested models failed to run or had difficulties. So in the end, we created the feature using the PyTorch Big Graph model, also known as PBG. Now moving on to the modeling stage. Actually, this follow embedding case is a task for creating features, so it is difficult to differentiate the modeling stage from the feature engineering stage, but you can think of this stage as the stage for optimizing the model. In our case, we use CPU to train the PBG model, but it had several problems, so we tried using the GPU and use it for training. And in this stage, we internally fixed the bugs existing in the code and carried out other tasks, including setting up a Docker image environment for training. And we reviewed the scenarios, so this could be used for serving. So this was a stage where embedding was prepared, so it could be put into actual use as a feature. And the scenarios that we reviewed for the following embedding consisted of two scenarios in which a similar user is recommended or the user's post is recommended based on similarity between users. As I have said before, because we needed a separate environment, we created a Docker image, and through a new cluster, we created a Jupyter notebook in it. We made the model run model engineering in the notebook. And because we completed doing the task through GPU, because CPU could not be used, so there was no problem in creating data and embedding for serving. And we saved the data in Redis so it could be actually used. But we ran into problems when we tried to actually use it. The problem was that in order to search for similarity, the similarity of all users had to be searched. So everything had to be calculated, not searched. Without being able to predict which user will visit, we knew that we could not calculate the visitor similarity with the entire user every time any user visits. If we think about the situation a bit more, what we could do was take the embedding of a random user and compare the embedding of this user with the data with the same form of embedding and get the similarity result that you see here. And what we did was that we implemented an embedding search engine which could search based on embedding, so that after creating the embedding could be searched in advance to get the result. Specifically, the difference is that it finds the result without directly comparing with the entire embedding, and this result could be saved in Redis so it could be used quickly. In conclusion, our plan is to make the recommended results in advance with the similarity we actually make through embedding, and then implement these to the actual service. Second is the case of offline recommendation. The creation of offline recommendations started from a request to supply our recommendation service through Smart Channel. Basically, we share the same recommendation model, but due to technical spec, there was a need to deliver the recommended list to the Smart Channel side in advance. The problem was that in the beginning, the system was designed without considering this batch type recommendation, but at the same time, same recommendation model had to be used, so solving this problem was the main task. So what we decided to do was that, as you can see from the image, we decided to separate the data necessary for serving from the existing task and carry out inference and provide recommendation. And this was possible because tasks belonging to different stages, such as data collection, analysis, feature extraction, training, and serving, were readily separated. And because we used a model that was already trained, we didn't have to do any further tasks related to data collection, data analysis, feature engineering, or model training. But we still have to make predictions about all of the users, not just a single user based on a request. So we carried out tests using the existing system, and it took too much time. And it was due to several factors. And we came to a conclusion that the problem was with resources, so we have to change the way the system is served. So we prepared a separate large cluster for serving. And we loaded all of the necessary data and made it so that all the predictions could be made at once. As a result, we made it so that predictions about all of the users could be made in bulk within 5 hours. And the result is organized in HDFS as a snapshot and then delivered to the Smart Channel. Because we are near the end, to summarize, as you saw from the previous examples, machine learning-based services are essentially composed of many complicated tasks with dependencies upon each other, and these tasks have to be viewed from a pipeline perspective. In order to separate each task, organize the dependencies, and make sure they can be executed periodically and continuously. And it is also important to make a visualization of these individual tasks. Automation is also important for the long run. So we have to think from a ML pipeline perspective to quickly find and improve the problems in the model and the infrastructure. For the last part of my presentation, I'm going to talk about our next mission. The areas we're trying to improve upon nowadays is related to the fact that test environment and the serving environment are not the same, and the fact that data and feature are spread all over. Currently, our development is carried out in an environment that is based on Jupyter, and the notebook is converted to an image and deployed as we prepare for serving. Many of the measures have been automated, but there were still some discomfort in development and deployment, and in order to improve these, we're trying to match the test and serving cluster and environment so the notebook can run without any difference from the development environment. So the ideal picture would look like this image, but the data for serving still has to be prepared. In order to solve this issue, as I have explained earlier, similar to embedding, we are preparing a common feature storage so that generated data can be used for serving without separate processing, reducing some of the cumbersome tasks, and we are working so that features can also be used for tests. That is all that I have prepared. I hope this will help a lot of people.